Cool, thank you. Thanks, Lydia. I'm no longer under 30, so I don't think that's relevant in this context anymore. So I'm going to talk a little bit about the work we do. Right? I think, as Lydia mentioned, we're practitioners in the space. We implement a lot of AI in manufacturing. But to give you a bit of context as to kind of what I'm going to cover out today, I'm going to talk a little bit as to who we are, the work we do, some of the challenges that we face in manufacturing, some of the reasons I really like manufacturing as a space to implement some of these new technologies. And then I'll take a couple of questions. And then I do want to leave you with a challenge at the end. And I think a challenge is the principal reason that is, if you ask me to talk, it's a challenge I often put forward to a lot of the new joiners at DataProphet. And I'm keen to put it forward to yourselves. So maybe a bit of context as to myself. As mentioned, I'm Frans. I'm the CEO and co-founder of DataProphet. Previously, I did my undergrad in natural science. I've done a postgrad in statistics, where I focused on convolutional nets all the way back in kind of 2012, 2013, before founding DataProphet in 2014. Right. I think it's been an interesting journey, right, with DataProphet, and I'm going to kind of expand on a lot of some of the key learnings that we've had in the application of AI as I go through things. But a bit of context as to us, we're predominantly based down in Cape Town. We team of about 50, kind of wide mix of different skill sets in that. Of course, data science is a foundation stone, but within that is the necessary kind of computer science and engineering, and it's the intersection of those three that we need in order to implement a lot of the solutions that we do, right? And we talk about our implementation principally at heavy industry sites around the world. We've done quite a widespread of implementations. We've implemented Japan, China, throughout Europe, in North America, in South America, and of course in South Africa as well. So quite a widespread. For our sins, we've been recognized by a couple of forums, including the World Economic Forum. We participated in the Advanced Manufacturing Stream. We'll talk large about the application of prescriptive AI, the potential value that this specific application can bring in applying it at manufacturing sites. Right? That top right-hand corner is where I'm going to spend most of my time in these first couple slides. I think the top right-hand corner is what's very important to me, is this measurable impact that we can have upon the manufacturing sites that we implement the technology. Right? It's not simple, and I'll talk about the challenges and how we've almost, the path we've gone in order to achieve those. But I'm very proud of the work that we've done in order to realize those results. Okay, so to sum us up in a nutshell, this is the problem that we look to address when we go into industry. Right? For those not familiar with manufacturing as a kind of idea or manufacturing plant, principally every manufacturing plant runs on a recipe. Right? It's the same kind of recipe that you'd use to kind of bake a loaf of bread, but they're making a car. Right? It's a list of instructions. In those instructions, there are a set of set points, or it's an instruction to say set the temperature at this level, bake that loaf for this period of time. Right? So there's a set of variables and parameters that you're specifying in that recipe. Right? Done right, if you do that right today, you make a good car. If you do it wrong, right, something goes wrong, you weld for too long, the contrast drawing is too high, you're going to make a defect, you're going to have to rework that vehicle, you can't ship it, right? And of course, you definitely don't, and if you do ship it, you need to call it back. Right? These are all about points of loss for manufacturers. They don't want to do that. They've got large teams at these manufacturing sites that are working on two sides of that equation. You've got a production team who's all about getting as many units that pass quality out at the end of the day, right? And you've got a quality team who's all about just preventing any bad unit of production leaving that factory, right? And they work extensively at these manufacturing sites to reduce this loss due to scrap or defects, right? Or defects. So that recipe is referred to as a control plan, right? And we look to optimize it. Now, there are a large number of optimization technologies already in play in manufacturers for some time, right? Principally kind of borrowing a lot of traditional theory, principally very narrowly implemented. Right? And we look to change that a lot with the solution that we've built. Right? So I'm going to dive in here a bit deeper, right? This is kind of the beating heart of a lot of our IP and our implementation of our solution. This is how we realize the value. But just, humor me, I've been running the company roles principally grant administrator, so I've been removed from the deep technical detail for some time. Right? But a lot of our initial work goes into connecting data, right? And laying the groundwork for them potentially model. So one of the nice aspects in the job that we have, and I think most of the team will disagree with me, but we do actually get to shape the data that we then go on to use in the model. So we get to shape that data into something that we want for the algorithm, and we get to solve both the data at the same time as the algorithm. Although that shaping of the data is a very difficult and complicated problem. Anyway, we're bringing a lot of that data forward. We are joining it all together. We're providing a context. And then we're pushing it through a solution that we developed called Prescribe. And principally, Prescribe is there in order to interrogate that data, interpret what are the different, what are the impacts that changes in parameters will have. So what are the different operating regions that factory operates in, right? Understanding that, and I think many of you familiar with the space will recognize that as a latent space, born out of a VAE adaptation, right? So in developing that, we can then interrogate that to determine how do you make small changes to your process parameters to move into a better operating region, right? There's a bit of supervision in the back end of that statement. Of course, we've got to know what are good regions, what are bad regions, so we've got to bring in that quality data. And in doing that, we can then determine what are the small set of changes to your recipe in order to avoid that defect from occurring. We've got to ship that back to a team of operators who are deeply familiar with the operating environment, but of course not data scientists, right? They need to get some set of feedback that they can understand in their day-to-day context. And that's typically is us presenting them with a ordered list of instructions as to how to change the variables that they're using to run their factory in order to avoid that defect from occurring in the first place. It's been a bit of a path to get here, right? And to give you a bit of context as to how we developed into this space, a lot of factories, well, a factory kind of reached out to us. They asked us to predict whether a unit was good or bad, right? To say, we've got this half-ton cast iron engine block, and we want to evaluate that half-ton of iron for defects is very difficult. And are there other ways that are simpler to evaluate it? And that's where kind of the predictive response was developed. We did that very successfully, and we then turned that into a prescriptive engine to say, actually, if we can predict using the process parameters that have gone into the production of that block, we can turn that around and say, what do you need to change today to avoid that defect from ever occurring in the first place? And this is where it is a prescriptive system. Right. So this is then kind of the North Star that we look at. So we've built this all. Of course, all of that is very interesting, but if it doesn't work, it doesn't matter. Right? And where we go in and kind of where we justify to our customers that they should be paying us some amount of money is off the back of results that we can achieve with the system when we deploy it. Right? To make this, so these are multiple deployments of our solution in a mixture of different spaces. You can see we've done quite a bit of work in gray iron foundries. That's where we've started. So in pouring of iron into different molds to prevent defects allows you to, of course, prevent the wasted energy that's gone into the melting of the iron that you then have to scrap, right? You typically don't work. Most gray iron facilities work at about a 6% or 5 to 6% defect. So for every 100,000 tons they're casting, 6% or so of those are going to be remelted. You lose all of the energy that's gone into melting it in the first place, and you've got to work it again. Right? We've done similar work. Well, we've applied the same solution in an automotive environment. You can imagine the highly automated robotic weld cells that go into the actual welding of the chassis of the vehicle together. Of course, if there's a defect discovered on one of those welds, it's quite a complicated rework process that system has to go through, right? And that all costs time, money, and effort. But it has to be covered somehow. Right? These are kind of, a lot of these KPIs or key performance indicators are key drivers to the performance of a factory. Right? Where those defect rates go up, they're incurring additional energy costs. Right? Where those defect rates go up, they're incurring additional material costs in it and labor costs in the actual work. Right? There is a large kind of definition that is frequently used in the governance of any factory called OEE, and that takes into context what percentage of your goods are passing your final quality. Right? And there are teams within factories working to ensure that they get the highest possible yield. Right? And it's fascinating, and part of the excitement and what I draw energy from in the day-to-day is seeing these different sites and understanding how they grapple with this challenge. Right? Gray iron foundries have a 6% defect rate. A semiconductor fab, so your modern kind of semiconductor fabs typically sit somewhere between 85 and 95% yield. So they have a 5 to 15% defect rate. 5 to 15% of the CPUs they're producing at the end of the line will be thrown away. Right? Deployment is principally running the same architecture. And that's been quite an important component for us. We see a lot of data science practiced in industry. Right? Many sites have their own data science teams. They're large enough that they can afford, and the kind of economics all work out. But what happens then is each site has its own kind of nuance. There's not a lot of scalable deployments of AI in different environments. Of course, for us to succeed as a business, we've got to be able to develop a system that we can repeatedly deploy. The generalizability of our solution is important for us to succeed as a business. And what's been wonderful for myself to spectate here is we've managed to do this across quite a wide mix of environments. Another thing that is very interesting, stands out to me, is I'm not an engineer. While we, of course, do have engineers on the team, we never present ourselves as experts in the specific process. We do not have foundry experts. We do not have weld experts. Yet we are able to shape the data and provide feedback to those experts that are in those sites that they can then take action upon, and we're able to improve upon the quality of the factory's performance. Right? And that, to me, is delivering on one of the promises of the application of data science or AI. Is that we can build experts, expert model or experts out of the data, right? And that was made most clear to me, in fact, in the furthest left-hand column where we did work in a world environment. It was for one of the German OEMs, right? They, of course, produce a lot of cars. They're very familiar with welding, right? They sponsor a huge number of individuals just to specialize in welding. They've spent a long time optimizing their weld environment. We as non-experts in that space were able to take the data, shape it into a space, run it through our system, develop a set of recommendations that they then implemented in their weld cells, and they realized a reduction in defects of about 50 to 70% in the various different tests that we ran. For them, it was a complete surprise, almost to the point of frustration, right? Because how can a team or not a set of experts improve upon the quality of the weld where they've been spending decades upon optimizing it? This is also another aspect that I love to reflect upon, right? Because it's not always obvious, and I think especially when it comes to the compute of large AI models, people do raise questions as to what is the purpose of spending all of that energy in a space where, you know, the expense of that energy comes at a cost. Kind of a medium to large foundry melts about 100,000 tons of iron every year. Right? At that 5% defect rate, we find that we can typically reduce that by half, if not more. Right? And that saves then the energy that's gone into the melting of that. That energy can be translated to carbon emissions. If you work in a country, it is principally carbon-fired country, and a not very efficient one, it translates into about 2,000 to 4,000 tons of carbon emissions saved each year. Right? And if we're successful in the work that we do, we get to implement this at a set of maybe 100 to 1,000 different foundries around the world, which as a small team, from a measure of impact, is fairly significant. And it's a kind of wonderful point just to realize as we go in the implementation of the technology. Okay, so just a little bit about context as to how we go about our work, right? Of course, we like building a product. Of course, we like defining it, trying to design something that is kind of clean and good. And that's us on the left-hand side with our end-to-end prescriptive AI. We've got to integrate it into the various different data streams that sit in a manufacturing plant. We've got to publish those up. We've got to join them together. We've got to make sure that the context is not lost in amongst all of that. We've then got to run it through an AI solution that we're trying to build in a pattern that can repeatedly deploy it, scalable and generalizable across different manufacturing spaces. Right? And then we've got to interrogate them for feedback that they can take action upon. Right? Because if they're not going to take action upon the outcome of the system that we're producing, it has no value. In order to do that, there's a huge amount in the digitalization journey, which is kind of much of our day-to-day. How do we actually get a set of data from a factory environment, navigate all of the complexity of that, and there's an immense amount of complexity that each different process vertical has, right? To give you a bit of context that we've got to, interface with, a lot of the semiconductor industry does not escape the process data of a specific machine for concerns around IP, and specifically the design of the chip. And so how can we optimize yield where they can't even escape the data from the piece of equipment that's sitting on the line, right? A kind of extreme other side of that is manufacturers still use logbooks, writing down data, right? So how do you interface with that set of data? How do you bring that quality information across, right? And so a lot of our kind of day-to-day, a lot of our man-hours go into actually facilitating this change at different manufacturing sites. Right? This is working with the operators, having them interpret the value of the data, bringing that site forward into a space that we know they can realize, but having to work with them to ensure that they kind of get ready for this digital work. There's a bit that we have to give in amongst all this. We are a startup in a very big industry with very conservative players when it comes to manufacturing. And rightfully so. Any manufacturing plant, you don't want to break it because it's worth a couple $100 million. Right? And so they're always sensitive in the introduction in any new technology. And they want to know that they can get some set of value. And to that extent, we're going to our results. And then there's also a lot of work that we're doing in order to understand when you implement the system, what does the post-installation look like? Right? Beyond just software as a service, beyond just maintaining the software, you've got a system that should be learning continuously. You've got a set of data that underpins it that is changing continuously, both from kind of the width of the data, so the different set of inputs, as well as the different effects that are being experienced in that data. Right? And so how do you maintain that type of system? And these are some of the problems that we have to work through in the practical implementation of this. Okay, so as mentioned, I'm not an engineer. I don't actually come out of an engineering field. I come out with more finance and more kind of consultative spaces, right? We as a company started back in 2014. We didn't start in manufacturing. We actually started in different spaces. Our founding kind of hypothesis was more centered around us being a set of experts in the field and looking to learn from a different set of verticals and understand where within those verticals we could create some clear set of value. For that, we've actually worked in a mixture of different spaces, finance, within finance, insurance, kind of within sales, and specifically call centers. But ultimately, we've now focused and we work in manufacturing now today. And since 2017, that has been our focus. A couple of very nice aspects out of manufacturing, having done work in other spaces that aren't necessarily available to them, that I like to reflect upon and kind of motivate for why the space has an immense amount of potential for very good implementations of AI. So that's always nice, right? That engine block, in fact, is one of the engine blocks that have come out of Foundry that applies our technology, right? So it ships to Detroit right? Hence the picture, and then it also ships to Mannerheim. It drives that vehicle, right? It drives that vehicle, right? It's very much, I thoroughly enjoy just being able to get onto site, obviously engage with various different teams, and then of course see the impact upon our technology, the impact that our technology has upon the site, right? And it's a continuous debate internally as to how the sites are actually using the technology too, right? One of our current internal conversations is, while we've designed this such that it can provide this clear instruction as to how to make a change today to avoid that defect, we're finding teams on sites actually using it largely to interrogate different scenarios or to learn from it, and then build bigger, different initiatives off the feedback that the system is providing them. Right? This is another Foundry environment. We spend a lot of time kind of walking through sites, engaging with the various different customer sites. It makes the whole system very much real to us. Right? I think then the first reason here, and it always strikes me as a bit of a surprise, this is a bit of research done by Morgan Stanley. It's a little bit dated at this time, right? So this is 2018, 2019. And by their estimates and by their research, manufacturing as a space has the most amount of data when it comes to just the sheer production. A lot of this data is just sitting on the factory floor. A lot of it is not being escaped into some central location, but the amount of sensorization upon any specific modern piece of equipment, the amount of data it produces is kind of immense. Right? Yeah, the scale of the data that is coming out of these environments is something that just presents a potential opportunity to say, if we need a lot of data, these are spaces that we could operate in if we wanted to implement good AI. This is obvious, but it's not always apparent in other verticals, right? No one debates that there is some causal aspect, right? So what I've described up here is a process flow through a foundry, right? Each block there represents a specific unit process, right? This might be the melting of the iron, it might be the pouring of the iron, it's the making of the mold, right? If you do any one of those things wrong, it may have an effect downstream, right? That's not a kind of, everyone accepts that, that there is this deep causal relationship that runs through these spaces. It's difficult, and I've listed a couple of points where kind of building that data to represent that entire process flows is complicated. But if you change something upstream, it's not a debate as to, and if you can measure and demonstrate that it has an impact downstream, that's comfortably accepted. Right? And it's in the application of other AIs and other environments and other process verticals, it's not always true that is something that you've got available to yourself. The next one is control is very complex, right? So the actual control of these systems is a very complicated thing. Most of the kind of narrow control loops that exist in a manufacturing plant today are done in a very kind of traditional kind of small number of parameters, physics-based pattern. And because of all that, they can only have a very narrow impact. So they specifically one or two parameters within a narrow span at a factory. But the interactions, as I've mentioned, are kind of very deep and far-reaching. If you do your moisture in your sand plant today, if it's running too high, and that might be an effect of moisture in the atmosphere, you're only going to realize that maybe in 10 hours time when you pour iron into that mold, and it knocks a part of sand off into the actual iron and forms a defect in that casting. Right? To understand that interaction, then to understand that potentially that can be corrected downstream with your pour profile, so how you pour that iron into that mold, is a kind of deep, difficult relationship to develop. Right? So what I'm characterizing here is in most factories they run what is termed statistical process control. Every parameter has a target. Every target also has a set of limits. You want to try and hit that target. It's very difficult because These targets exist in the natural world, so you're going to land close to it, but you're never going to hit it exactly. And then you want to be between those two boundary conditions, right? When they set up that statistical process control, when they do that definition, they're typically considering every parameter independent of the next, right? I mean, how else do you do this analysis with the traditional approaches? And so what we're showing here is two process parameters, and you might be operating what is termed in control, so within the boundary conditions of both parameters, and still producing bad parts because the interaction between those two parameters isn't well defined within your traditional techniques, right? Now, of course, when you get into the hundreds or thousands or tens of thousands of process parameters that govern the control of the environment, that interaction and discovering how to accommodate for that complexity becomes very difficult. Right? That all sets us up for success in the application of our solution. It's not without its challenges. All right. So when I think about that, this is a kind of a legacy that we have to work with. Data in factories, and I think data in many different industries has been built for various different reasons. And optimization typically is not one of them, right? So when we go into any factory that build data such that they can run their machines in control, we consider control just to be that narrow process or that narrow parameter. Right? So they build that data. What that means is that data is typically silent. It's not connected to data upstream or downstream of it, right? It was never designed to be connected to data upstream or downstream of it. And so there's a big piece of work that we have to do in order to lift them off this data aggregation control level. And typically there's a bit of a path that we have to go through to say, well, we're going to bring all your data together, we're going to show it to you, so you've got confidence in your data, right? You then typically will go through maybe a query, which is a very human driven process. And this is where data scientists at the customer side will develop a hypothesis, test it with that data. But we want to get them into the mindset of actually going one further, whereby we're doing an AI-driven analysis and ultimately at some point potentially some self-directed feedback for the systems that we're putting in. Right? What that means is we've got to take them from a data environment which they've built and developed to allow them to have very narrow control over machines to something that facilitates the holistic control of the entire factory, right? And for them to trust that their data can represent the entire factory. You know, we can take action, or they can take action off the recommendations of an AI system that can view that entire factory through that data. So it's a movement away from just control to optimization through your data. And the hard point that we always have to navigate with customers is to say, we're now going to put your factory at the control of an AI that has learned off your data. Do you trust it enough? And it's not, the trust is in your data. And do you have that trust in your data today to turn your factory's control over to it? 9 times out of 10, the answer is no, right? And we've got to try and get them to a point that they eventually, within some scope, say, yes, actually, we're beginning to believe this. Right? This is one of the big problems that we face, is the contextualization of that data. Right? And just to kind of expand upon this a little bit, so you've got units of production, right? So each one of these blue aspects would represent a unit of production. If you're in a discrete factory, you're making a car or an engine block. If you're in a continuous factory, it's typically a liquid circuit or some such like that, which is continuously moving through the circuit, right? But you can discretize that. So that's moving through time, right? And a set of sensors are observing that material through time. Most data, as mentioned, is sitting at a sensor level. It represents that sensor's experience in time, not the unit of production's experience through time under those sensors. And so there's a pivot upon the data that we always have to perform. This is a complex ETL process that we go through at every production site, right? Where we've got to take data from representing that sensor's experience to data that represents that unit of production's experience. And it is difficult for a wide mix of reasons. Right? You can't put a barcode on 10 tons of molten iron. Right? You've got to somehow infer which a ladle of iron that engine block you've wound up at the end of the line has come from. Right? And you've got to trace that back through that process. And that's true of a wide mix of spaces. Traceability isn't so simple as just a barcode. You've got to do some matching through a process, and you've got a whole mix of different kind of competing things that you've got to contend with, like buffer zones in a manufacturing environment. Right? And this is an example for some of the data points that we'll go in and we'll look to uplift and collect from manufacturing sites. So you've got your process data, you've got your quality data, and then this third force, which is your traceability. How do you attach those 2 points together, right? And you'd be surprised that for many of the spaces that we're operating in, those points of data are not attached and haven't been attached together before. And for very good reason. Again, you've got two teams that run you've got many teams that run a manufacturing site, but principally in our world, we engage with two of them. One is the production team, who wants to make sure that the process is running well, right? And the second is the quality team, who wants to make sure that nothing bad ships from that factory. And they have built separate systems with separate pieces of data to ensure that they can do their work. And you've got to bring those two forces together, right? And you've got to match that data. And there are many challenges along the way in building that contextualization, right? And then there's a big piece of work, and this is true, I think, in every application of AI across every space, of saying, well, we've done this work, we've brought this data together, it represents your factory. You're now confident that it does represent your factory. We can now run this through the solutions that we've developed from the AI perspective, the prescriptive AI models that we've built, right? And we can provide you a set of prescriptions or points of advice back to your team. And at some future point, right, or some point right now, we're going to ask you to change the way you operate your factory according to the recommendations that our system is making, right? And we expect that this is going to improve the performance of your factory. And it is a very big ask for any startup making of any large manufacturing environment for them to make those changes, right? Because, I mean, the easy pushback is to say, well, you are not experts in this space. Why should we trust the results that your system is producing? I mean, that's one of the pushbacks. The other pushback that we get, and it's a valid one, so say, no, well, some of this is confirming my intuition. I don't necessarily see the full value of the system, right? And of course, it will confirm the intuition of some of their experience because their intuition is not wrong. It's right. It's a complicated change management process that we have to navigate through in the implementation of the system to support the improvement of these factories. It's engaging with a wide set of individuals, operators, process engineers, plant managers, communicating to them, understanding how do we present information to them in a pattern that they can put their trust in that information and then ultimately take action. And it, for us, is one of the most complicated, as much as the science, the actual implementation of the algorithm is very interesting, and it's what kind of gets us to the office each day. One of the big complicating components of just the day-to-day of the business is working with customers to run through this change management, right? For them, they're not interested in the fact that it's a modern deep learning algorithm, right? They want to know that if they follow this instruction, it's not going to break anything in their process, it's not going to make anything worse. In fact, it's going to make something better, right? And how do you do that with a system, and especially given that we are leaning into deep learning techniques in order to get the performances that we have? How do you do that with a system which is not explainable, right, at its deepest level? So there's a lot of this iteration that we go back and forth and listening to concerns, adapting, changing, the guardrails that we have to put in the system, the kind of constraints upon it that we impose, and there's kind of just a fair bit of just engagement to listen to those concerns in the implementation of this. Not simple. Okay, so I'm going to pause now for questions before I put forward that challenge. Right? This is us. We are a set of human beings that do have fun outside of the ordinary course of work. If you're interested in joining, please do contact me or just take a look at the website. Right? But yeah, I'm happy to take a set of questions before I get into.
I'd like you to reflect on how you get into an organization. Do you typically find you're more successful if you introduce from senior management level, or are you more successful if a quality engineer says, hey, I've been reading about this stuff and maybe we should try it, because your solution is a threat to the existing team?
It's, yeah. Okay, there are lots of teams. Some teams are threatened by it. I don't want to, mince those words. Right? Some teams are threatened by it. For a quality team, it should be assisting them to do better work. But specifically to your question, this is innovation work. It's typically brought in from senior management. Senior management, from our perspective, is either kind of central management or plant management. But there are multiple teams who have to sell upon this, right? So if it does arrive from that level perspective, we have to be careful that we do bring the other teams along for the journey. And this is also that change management process. So typically more successful from the senior management perspective. And the reason that we find is the senior management team can say to their teams that report into them, I want you to test this. And if the system goes poorly, it's not on you. Right? So they give them the space to do the experimentation. If it's bottom up, right? That team is always at risk that if the system doesn't go well, it's their kind of heads on the line, right? So unless their kind of management structure facilitates that, it's difficult for them to actually implement and take action upon the system, right?
You mentioned that you use the bad wells by like 5%. What changes did you make to actually achieve that? And also, how do you go about evaluating the fire molds for that fire mold? It is expensive to evaluate how it actually optimize the wall.
Yeah. Okay. So the world environment was an interesting one, because in those different spaces, the width of the data, the number of parameters varies dramatically. Weld, as a weld cell, I mean, we're just looking at 6 different parameters. I forget the specific list, but the current and duration, and lift height are a couple that I can recall, right? So those are the parameters we're affecting. We're just 6 parameters. What gets quite complex is that you typically have a couple 100 or 1,000, 2,000 different weld locations on the chassis of the vehicle. You want to optimize the specification for each of those set points and control limits of those parameters for every different weld location. And you do want to adapt that per a weld. So you've got a understanding as to how many different cycles that robot has gone through. Right? And so those were the parameters we were specifying. We were providing that steady update as to how to make changes between each cycle as well. And we're doing it across the full fleet of different weld locations upon that chassis. Right? So interestingly, no movement information in that. So the positional information of the robot wasn't considered. We're purely looking at data off the weld head. Not sure if that answers that first question.
And you get the data from the robot itself. You get how many cycles the robot has welded.
Yeah. So I mean, in that specific case, we're actually just looking at the number of cycles. So it's just count, but no positional information off the robot. It's mostly that data. Those parameters are largely confined to the robot head. Right. The second, sorry.
Second one is, you said you're actually evaluating the quality of the final product against to optimize against something, right? So
yep.
How did you evaluate?
Yeah. So the sites have different quality inspection sites, quality inspection stations, right? Typically, a kind of gray iron cast will undergo a visual inspection, right? So someone will look at it to say this is defect, this is not a defect. Larger blocks in your engine blocks, you don't want subsurface defects, you don't want cavities that will deform the cylinder at some point. So they may undergo some X-ray or some ultrasonic testing, right? But they are quite large blocks, so it's very difficult and quite time expensive. So typically not 100%, not every unit inspected. The other aspect is you cost product. will undergo some machining at some later date, some CNC machining to clean the surfaces. And at that time, there's also feedback saying when we machine down the surface, we found this cavity. Right? And those are the various different points of feedback. Ideally, this is beyond the scope of any work we've managed to achieve. It would be great to also look at warranty claims to see if at some future date that vehicle failed because of a defect in that engine block. But that's nothing we've achieved, and you can imagine traceability on that data. Not right now.
I have a question more on your digitization step next in the AI. I imagine some of the companies that you work with initially, with their legacy systems, the data they capture isn't that great. Do you create your own, like in-house, do you create your own interfaces for them to capture data, or do you just integrate with their existing systems? Because I imagine you probably met with some resistance, particularly in the automotive industry, when you want to totally override the way they do things at an additional cost.
Yeah. I mean, you hit on a very big point. There's this huge kind of industry of IoT in automotive that is trying to understand this problem, right? Is to say we want to leverage the existing data infrastructure, but is it sufficient for some objective? The way we go about it is we try and leverage what they do have. So we're going to integrate at the kind of higher levels. A lot of factories there's an ISA 95 standard as to, are you connecting to the sensor, or are you connecting to kind of a central database in an MES type system? We're trying to leverage the existing infrastructure, but to give you a very real world experience, if you've got a handwritten logbook, you can't interface with that. So you've got to then implement some digital interface that station can now capture that information digitally. So that's simply a keyboard. Yeah, so we've also got that system, right? And that's actually, I didn't dive into it, but that's our Connect system where we've got that whole integration there.
Okay.
It's a tricky thing because there's a lot of IoT out there in the world. And the way we think about it is actually we're an AI first, IoT second house, right? And that means the way we've defined a lot of our IoT architecture, infrastructure, is in support of the objective of implementing prescribe. Right? And that just kind of gives you quite a narrow focus as to what are you going to integrate into. Go.
Can you talk about the challenges involved in starting working with businesses before you have any results on your systems to convince them, back in 2017?
Yeah, I think the best way I can characterize this is in a piece of work done around, it's termed crossing the chasm, right? Which is to say your market has a population of different individuals in it. And those different populations can be, for the purpose of this, can be grouped into, you've got your innovators, your early adopters, your early majority, your late majority, and your laggards, right? Your innovators are a set of companies or it's part of the market which will say, I like the idea that you're presenting. I know you have no results, but I'm willing to pay off the back of just an idea, right? And they're the small minority, right? I mean, I don't think any hard science went into it, but it's 2.5% of the market or something like that. And that is the group that you've got to find, right? And you've got to realize that most companies, the vast majority, so even your early adopters and your, they're going to wait on you having at least one result, right? So it's all about saying, okay, for this first group, we've got to find a set of innovators who are willing to accept this on an idea alone. And then once you've got that set of innovators working with you, you've developed a set of case studies, you've got some results, you go to the early adopters, right? And they still will want to say, look, this is new. I'm willing to test it on a case study or two, right? And then your early majority arrives when they see all their peers are beginning to do it. And so it becomes a bit of a FOMO type situation where they say, okay, other people are doing it. The late majority do it because they have to stay in the market, and your laggards fail, right? But starting a business with a new technology, find this set of innovators, right? Cool.
Over here.
Testing. Thanks so much, Frans. That's a great presentation.
I have two questions. One is, you spoke a bit about your survey design briefly and how it ultimately flows from compliance data. Do you augment in special cases with your own hardware where you tap into areas of blind spots at all, or is it purely contextualizing that? And that's my first. And I suppose the second, my question is, how competitive do you feel South Africa is in terms of, as an industry, performing on the global stage with respect to data science, considering that DataProphet has expanded into other markets? What is distinctive about perhaps DataProphet's solution as a South African-based company, or perhaps as an industry that sets us apart?
Okay. Let's consider questions. The first one around adding principally additional sensors, things like that. Typically, we don't do that. It's quite a hard layer in terms of if there are companies that specialize in just adding those sensors. You're introducing sensors into very difficult, environments, factories, furnaces, things like that. If you pour multiple on the sensor fails, and we've got to replace it, and that's a whole business. So we don't get involved at that level, but the blind spots is something we can and we have provided feedback on to say, especially when it comes to the interrogation of that latent environment, is that we can say, look, we're failing to separate over here. We suspect there's some blindness in the data, and then it's a close engagement with us and the science expert team to say, we're blind to whatever's going on here, and can you interrogate that? And it might be additional sensorization, right? But we don't put those sensors. We'll work with some third party, or rather the customer will bring those from a third party. Second question was centered around, sorry. Competitors to South Africa. Yeah, it's a good question. And this has changed through our history, right, from answer. I think from a talent perspective, the one thing I really like about data science is it is fairly open and accessible to the vast majority of the world. I mean, the talent that you don't need super specialized compute infrastructure, right, to build most models, right? Not the very, very large ones, but most, right? So it is accessible. I think the talent that we have in South Africa is very much internationally competitive, right? So we can and we do compete internationally, and we produce results that exceed some of our peers at an international level. So that's proof in and of itself. Where I think it's interesting for me to have reflected upon us, we're a set of South Africans prior to COVID without remote working. It was easier to build a larger team with better talent, I think, in South Africa than it would have been in the US, especially when you start serving these niche scenarios like manufacturing. You can imagine, if you're a US AI startup, you've got to contend with a Google level salary, right? Which you can't. Here, we're less subject to that effect. It's not to say there aren't some of the big houses here. And it's not to say that they do pull talent out of the South African market, but it is to say, I think there's more very good talent available for small companies here. Right? There is a bit of a rebalancing that we have gone through COVID in terms of remote work available for data scientists. And we've seen that across kind of our team across the industry as well. Right? But I think us being lucky and starting maybe before COVID, we got to build a more mature system than our competitors, because we are more mature and ultimately better performing system because we had access to a larger pool of better talent than our competitors in our space. There's a lot to that. Right? Yeah.
Cool. So I think one more question, because Frans has a question for you. Sorry, the one behind you first.
I identify the points that you made that it's very difficult to sell the process control systems to the customer. I actually had that issue once. Would it not be possible to kind of brute force interpret the AI control system to generate response surface models, right? I mean, multi-dimensional response surface models, and then compare that to whatever current control system that they've got, whether it's a API, NID, or one particular control system, to show that the responses between the AI one and the current ones are giving fairly similar outputs. So there's a way to justify it.
Yeah, it is. We do it a bit more brutish fashion, right? Which is to say, let us run a commissioning test with multiple unit processes controlled by our system, or at least influenced by our system, and let us demonstrate that against your current performance in terms of your quality. And if that outperforms, then is this not better, right? It's the British AI approach of the application of AI across a mixture of different spaces, just to say we've got a better result, so the system is better. And I think it's quicker to achieve the general acceptance, right? It's not, you know, there are different approaches to doing this change management / convincing, right? So it's our approach. It's not to say it's best. It's a bit brutish, but it kind of gets us to where we need to go. Right?
I'm not sure if you're able to answer this question or not, but do you feel that the universities and the various academies producing
Yeah, it's a fair question. I'm going to just attach a dozen different caveats in terms of this is my narrow experience, right? I think, you know, our experience with new graduates is they know the theory best, right? And so we must listen to them from a theory, new ideas, which talks to your aptitude. But then there's a fair bit of training that we must do in order to kind of ensure that we as a team build a system that can be confidently trusted and productionized, right? So this is, how do you work as a team, right? And when working as a team, how do you communicate? You know, who is the person on the other side of the table that you're communicating with? Do you understand their specific concerns? Are you listening to them? It's all of these kind of skills that are necessary for the actual implementation in the field, which are something that needs to be trained on the job. I don't know if it's fair to put it on the universities, right? That's an additional caveat, right? Cool.
Yes. Okay, so I think that concludes the questions part. I know that Frans has a question for you guys.
Yep. So this is a challenge I put forward. Indulge me. It's a little bit off beaten track, but it's typically a challenge I put forward to a lot of the new joiners at DataProphet, right? And something I want to leave you with, right? I'm curious as to whether you think we already have an algorithm for this. I know that's max specificity, but you know, it's a point to think about. So, do we have already today an algorithm that will realize artificial general intelligence? There's a lot implied in that question. Of course, it assumes that you accept that we'll get there, and it means also that you think we get there soon. Right? To give you a bit of context as to it, we know that neural networks are universal approximators. There are a lot of caveats attached to that, but a single layer is sufficient to represent any function. Right? There are some caveats, and I do encourage you to read into those caveats to it. And then the question falls to you as to whether you think human intelligence is a function that can be approximated by a universal approximator. Right? Again, do take a look at their work. Right? Maybe infeasible, so there's some reasonable pushbacks upon this, right? But then the contrary is this evidence for the scaling hypothesis that we do see, where kind of simple architectures just scale with more data and more compute get and continue to get very good results. We haven't broken this curve, right? We haven't seen this error rate deteriorate as we've scaled the data, right? And we are finding these meta learners out there, right? it's a challenge. I like this as well. There's a very interesting, if you enforcement learning, you'll know Richard Sutton in the space, right? The better lesson, and it's something always just to think about. It's a point that I think about in the context of our work as well, right? But I'll leave this up for you to read. I think it's a good point of reflection that he's had upon his experience, and he has a lot of experience in this space as to what is the best approach in developing state-of-art AI. Right.
Let's keep this thing on. Is there anyone who wants to take a stab at answering that question? Do you think no, but AI, we already have the algorithm.
I think we have a great person who can answer.
So I believe it's somewhat mathematically established that you can't use one model to generalize to every problem. I think the theorem is called the free lunch theorem. So that's the first
Challenge on this.
The second thing, I mean, there are already like established algorithms that can be applied to several tasks, but a general intelligence is, as again, it's mathematically infeasible. But then you also mentioned the fact that if you just scale simple architectures, I'm inclined not to believe that for some reason. Well, the reason I would propose is the fact that unless you impose some kind of like unless you try to mitigate problems of gradient loss and gradient explosion, that should not that drop shouldn't check out. So I'm inclined to be skeptical at that job.
I encourage you to read that, right? And very much that point around gradients, gradients disappearing, vanishing, the vanishing gradient problem, the exploding gradient problem. I mean, all the regularization, all of those pieces of work are reflected upon in this statement, right? Your point around the no free lunch, not talking about the best, the quickest, the best algorithm.
And then I think it's all points around. I guess what you mean by the second point to start with that. As to whether mathematically intelligence is not feasible.
So the free lunch theorem, as far as I understand, is that in order to generalize to several tasks, you do specialization on individual tasks. So, I mean, there are sort of one approach that comes to mind that aims to make one optimization algorithm applicable to several tasks are heuristics. But again, they're particular to like discrete combinatorial optimization problems, and if you're talking about a general intelligence, that's if it's feasible, it's certainly not something that exists today. That's
a strong assertion.
That is a strong assertion.
I challenge that, but it's worth it. But we can chat afterwards as well. It is a very strong assertion. I mean, do you think human intelligence is not a function that can be approximated?
Well, I would say we don't understand neuroscience well enough to make an informed decision there, I would think.
How we think does not work in the long run.
Sorry, repeat that.
How we think does not work in the long run, which is just to quote the back end of that first sentence, as a means to try and properly interrogate our own selves to develop our intelligence might not be the best approach in terms of producing state-of-art AI. Better understanding of our own selves. Yeah. Anyway, thank you. Yeah, I mean that's what he's saying in the first sentence.
Sure.
This is going to be the last one. I know we're doing the break.
So maybe I guess I can't go with another question, because I guess this kind of conversation is final. I don't know if you're familiar with the work of Thomas Nigel, who talks a lot about the emergence of conscience and, you know, the evolutionary process explained through causality instead of correlation, meaning we understand our own consciousness merely as a function of correlation, not causation. And so I guess inherent in this question is emergence sufficient to produce general AI? But I would ask, if we cannot explain how this emergence process produces a general AI, is that still valuable? And so the goal here is, do we want to create a general AI for the sake of general AI, or as a vehicle to understand consciousness and our own way of thinking?
Yeah, I mean, I'm of the view that intelligence is valuable in and of itself. Doesn't matter how you made it, right? But yeah, fair enough, right? If we don't understand, is it valuable?
Okay. I think we do need a coffee, so I'm going to ask you to give a big thank you to Frans.